And I'll just start. So let's skip past some of the group 2 stuff for now. And if we start with the group 7, so what I've done quite intentionally, I've tried to follow specification points quite clearly. I've gone by AQA as that seems to be the majority, but a lot of this stuff is overlap between AQA and OCRA, which I believe the majority of you are. Edexcel is pretty much the same as AQA. For OCRA, the one thing that is slightly different is you don't need to know about the reduction reactions that we're going to talk about in a couple minutes with sulfuric acid. So for the OCRA people, most of the stuff we're going to go through is exactly the same. If you haven't come across any of the reduction reactions with sulfuric acid, then don't worry, you don't need to know those. But everything else is common across them. So if we start off with a very basic overview of what we need to know about the halogens, group 7, the very first thing that is super important for pretty much all of these questions where you have to describe reactions is you're going to need to know how they look. And you don't just need to know how they look in one form, you're going to need to know how they look in different forms depending on the question. So the first thing you need to be quite aware of is that in their kind of natural state, how they exist at room temperature, they're going to always get darker and they're always going to get denser as we go down the group. So we start off with fluorine, pale yellow gas, or sometimes you could say pretty much transparent if you look at this picture here. We've got chlorine, greenish gas. We've got bromine, red-brown liquid, and we've got iodine as a black solid. What you also might want to know is how the vapors will look. So for bromine, we've got kind of red-brown gas as well. And for iodine, we've got a purple gas. So the vapors for iodine, notice this is the weird one. It has a slightly different color as a black solid, but as a purple vapor in the gaseous state. And we also might need to know how these look in solution. So chlorine is pretty much colorless, somewhat pale green. Bromine is also exactly the same, also red-brown. Iodine, again, is the weird one. So iodine is as a solid at room temperature, black in color. And the gaseous form is going to become purple, like you can see in this photo. And in solution, it's going to become dark brown. And that's something that we might need to remember as we go through some of these reduction reactions in a couple minutes' time. So make sure if you weren't sure about these, you've taken a note of these colors. And this is something that would be kind of very important to memorize. And the key one to keep in mind, iodine, it changes color between the forms. So if we start off with the very obvious kind of first point, we know that as we go kind of down the group for the halogens, and we know what the different ones are. So we've got fluorine, chlorine, bromine, iodine. These are the main ones, the reactions you need to know about. Astatine and tennessium, not really covered. So for these four, we're going to be focusing mostly on today. We know that they always have the outer configuration S2P5. So like 3s2, 3p5, 4s2, 4p5, they always have 7 electrons in their outer shell. And with every one we go down, we have one extra filled main level of electrons. Now, this is taken straight from the AQA textbook. What can we see is the problem here with this diagram? What's not going right? So quick look, this should be pretty obvious, but we know that as we go down, the outer shell is getting further away. We've got one extra shell of electrons, and well, that's pretty right. It's showing how it gets further away. We've got an extra shell. So what is the problem here? What has AQA got wrong? And if you have this textbook, it's the Oxford textbook. You can go back and check after this. What's the problem here? Yeah, it's given it as S2P6, and clearly it has to be S2P5. They all have 7 in their outer shell. So make sure if you do have this textbook, make sure you don't remember that wrong. It's always going to be S2P5. But as you can see, key idea here, which they were right in the textbook too, the outer shell is going to get further away. You've got one additional shell as you go down the group. And that's going to be quite important when we start to think about the properties of these halogens and how they change. So if we start off by thinking about when they melt or when they evaporate, what kind of bonds are we breaking? So if we think about we've got one of our halogens, and so for example, we've got say chlorine, and we've got the Cl-Cl bond between them, and so kind of one electron being shared. What can we say is this bond between the two chlorines, is this the one that we're breaking when they melt or evaporate? No? And so what do we break instead? Yep, van der Waals forces. And what particular kind of van der Waals forces? Yep, we've got the London forces, exactly. So for the next question, let's have a think about what these London forces might be and what they might look like. So how might they come? Where might they come from? How might they be structured? So let me just try and move on to the relevant question. So we've got one here. Chlorine has a low boiling point because the forces between the molecules are weak. Explain how these forces arise between molecules of chlorine. So we're quite sure that we need to be talking about London forces here. And when we get a question like this, I would first try and explain what the forces are. So I would describe what kind of forces we're talking about. And I would then start to refer to maybe how they arise. So for this one, I would start by describing what we're talking about is a type of van der Waals force. We're talking about London forces. And I would say where they start to originate is we're getting random movement of electrons in one of the molecules of chlorine. And that random movement of electrons is going to produce a dipole. So we've got imbalance in electron density. There's random movement of electrons. And the movement and fluctuation of electrons to one side or the other side of the molecule of chlorine is going to result in a temporary dipole. What we're then going to say is this temporary dipole can then induce a dipole in a second molecule of chlorine. And there's going to be a temporary attraction between the first instantaneous dipole and the second induced dipole. So if you imagine we've got a chlorine molecule, if all the electrons move over to one side, that side is then going to become temporarily more negative. That is going to induce another chlorine molecule that's close by. The relevant side to that, that's quite close, is going to become temporarily positive, and there's going to be the attraction between them. That is the London force. And is everyone happy that these are the molecules and these are the forces between the halogens? This is what determines the melting and boiling point. Yep, so we're confident with this, right? Well, with that in mind, let's have a think about what we know about the properties. So we know that we've got these kind of random electrons movements, and these are causing the intermolecular forces between our molecules of chlorine. Well, what is going to determine how strong they are? What is the biggest factor determining that? Yeah, the number of electrons. Okay. So does that make sense? The number of electrons is going to determine how large these forces are. Because where do these forces come from that determine the melting and the boiling point? It's from the random movement of electrons. Now, if we've got more electrons, they're going to be kind of a much bigger dipole being established, a much bigger imbalance in electron density. And so we're going to have stronger forces, higher melting and boiling point. So we can look at the trend here for the halogens, and we can see that kind of as we have more outer shells, as we have more electrons, we're going to have higher melting points and we're going to have higher boiling points because we have these stronger London forces. And does that seem quite logical? Easy to understand? Yep. So this is one of the ones, no need to memorize, we're just going to follow. If we think about the next thing we've got here that we need to know the trend about, we've got electronegativity. So what do I mean by electronegativity? What do you understand by that? Yep, exactly. So we're thinking about what is the ability for this atom, it could be anything, it doesn't have to be a halogen, to attract a bonding pair of electrons or to attract electron density towards it in the covalent bond. So if we think about this trend here, what we can see is that for these halogens, fluorine in particular is the most electronegative. It's desperate to attract all of these electrons towards it. And as we grow kind of down the group, they become less and less electronegative. Now, chlorine is still pretty electronegative compared to other elements. So halogens by default are pretty electronegative. But as we move down the group from fluorine, they become less and less able to attract a bonding pair of electrons. So they're less desperate to attract electrons. And if we think about the reasons why, so if we go for an example, and I was to talk about, let's say, a hydrogen halide. So if we talk about, say, HF, that's the first hydrogen halide, and we compare to, say, HI. So out of these, fluorine and iodine, which one is more desperate to attract the electrons? Yes, fluorine. And if we think about the reason why, well, our fluorine is going to be much smaller than our iodine. So iodine is going to have far more outer shells of electrons. And as we have those far more outer shells of electrons, the first change you're going to see is that the difference between the nucleus, so the positive nuclear charge that is doing the attracting of the electrons, and the bonding pair that's going to get further away. So the distance between the nucleus and the bonding electrons is going to get further away. And we've also got more inner shells between them. So the reason why the distance is getting further away is because we've got these additional shells. And as we get further away from the bonding pair of electrons, and we have more additional shells, there's going to be more shielding or more electron-electron repulsion. And that's going to reduce the ability of the nucleus to attract the bonding pair of electrons because they're further away and they're also experiencing shielding, electron-electron repulsion from the inner shells. So if we keep that in mind, and we think about the fact that these elements at the top, so fluorine and chlorine, are more electronegative, do you think it's going to be easier for them to be an oxidizing agent, or do you think it's going to be harder? So if something is more electronegative, do we think it's going to be easier for it to be an oxidizing agent, or is it going to be harder? And so to start with, maybe have a think, what do we mean by oxidizing agent? A lot of these words, I think, sometimes confuse people. The first thing I would want to think about is what do these words themselves mean? So for oxidation, what's happening is we're losing electrons. So if something is an oxidizing agent, it's the thing doing the oxidation. It is causing something else to lose electrons. So if you're an oxidizing agent, you really like to steal electrons. The oxidizing agent is the one who steals electrons. It's really obsessed with electrons. So just like fluorine here, very electronegative, very obsessed with electrons, it is also very capable of stealing electrons. So generally speaking, when we say something is more electronegative, it's also a better oxidizing agent. And this is something that you can kind of figure out from first principles. So fluorine, because of this distance between the nucleus and the bonding electrons, because it's so small, it's really desperate to attract the electrons. It's more electronegative. It's a better oxidizing agent. Does that make sense? So it's easier, it's more capable of stealing the electrons. So fluorine is going to be the most powerful oxidizing agent. It's really, really capable of taking the electrons. Iodine is not very electronegative, and it's also not a very good oxidizing agent. So iodine is not very able to take the electrons. So everyone following that. Yeah, okay. So let's start with this nice and easy question. Which property increases down group 7? And as soon as you have an idea, just direct message. Or you can message for everyone. So, yep, answer is going to be B. And if we think about first ionization energy, now I didn't go over this, but what happens to the first ionization energy in Y? So the answer is no, it doesn't increase because as everyone said, boiling point increases. But what happens to the first ionization energy in Y? Yeah, it decreases as attraction decreases. So you would use the same reasoning to describe ionization energy exactly the same way as you would be talking about electronegativity. It's the same factors. So first ionization energy is going to decrease, not increase. Now, if we think about the reactions that can take place between these halogens, so what we're saying is that a more reactive halogen is always desperate to take the electrons. So a more reactive halogen is always going to displace the less reactive halogen from its salt. So if we have, for example, sodium bromide, NaBr, well, chlorine is higher up, it's more reactive, and so chlorine is able to take the electrons from the bromide ion. It is able to act as an oxidizing agent and is able to become the Cl minus ion. So fluorine is able to act as an oxidizing agent with anything, and that's why we have kind of fluorine in this cartoon here. Chlorine is able to be an oxidizing agent for anything below it, like bromine or iodine. So if we think about this reaction up here, chlorine plus NaBr is going to make bromine element and NaCl, or bromine molecule. Well, what do you think is the color change we're going to observe here? Thinking about what we spoke about at the start. So what suddenly are you going to notice as a color change? What's going to be the difference here? Yep, we're going to see a red-brown color. Very good. So the bromide ions, they're not going to be they're not going to have a particular color. We've got Cl2, which is pretty much colorless. And you could say perhaps it was pale green solution, but pretty much colorless. And we are now producing bromine. So chlorine, which is more reactive, more electronegative, better oxidizing agent, is going to take the electrons from the bromide ions and it's going to produce bromine molecules. And so we can see once we've produced bromine molecules and they're present in solution, we're going to end up with a red-brown color. So what is the main change you're going to see with this reaction? You're going to see a red-brown color appearing. Does that make sense? So if bromine is oxidized, it turns red-brown. So, well, not bromide, we're talking about bromide ion, to be fair. So not bromine, but bromide ion. And yes, when it becomes bromide, it is going to turn red-brown. So be very careful with that. I was looking at some of these questions to think about where people often go wrong. That was like really commonly written in the, I think, like mark schemes. They were looking for bromide, not bromine. So make sure you have that. Now, so far, everyone happy. No one lost. We'd get all these correct. Right. So now we're thinking about sodium halides. So we've said that when we have the actual halogens, so not the halides, but the halogens. So when we had like FCl, we said these were oxidizing agents. Oxidizing agents because they wanted to steal electrons and become negatively charged. We now have sodium halides. These already have an extra electron. They're negatively charged. So what are these going to want to do? What kind of agent are they? Reducing agents. So usually these halogens are going to want to steal electrons, and so they are oxidizing agents. The sodium halides, they have already got the extra electron. They're negatively charged. Now they're going to be reducing agents. Now think about which one of these is going to find it easiest to give away their electron. So if we said from the beginning, fluorine is always desperate for electrons, which one of these is going to find it easiest to give away? Yep, it's going to be iodine, but remember, don't say iodine. This is the iodide ion. So the iodide ion or the bromide ion is going to find it much easier than the fluoride ion or the chloride ion to give away its extra electron. For the exact same reason as we talked about the electronegativity trend. As we get bigger, the outermost electrons are going to be less attracted by the inner nuclear charge because they are further away and because there are more shells of kind of inner electrons that are shielding or that are giving electron-electron repulsion. So for the sodium halides, the ones that are best at giving away electrons, the ones that have the best reducing power are going to be at the bottom of the group. So iodine is the best reducing agent because it's the easiest one to give away its electron, iodide. But fluorine is the best oxidizing agent because it's the best one to take electrons. And once it's taken its electrons, it doesn't very easily give it away because fluorine, it loves electrons. So are we happy to remember these three properties? Fluorine being the most electronegative, the best oxidizing agent, but fluoride ion being the worst reducing agent. Okay, cool. Right. Now, if you remember that, and you remember that well, you can then make sure you're getting these questions right about concentrated sulfuric acid. So before we go on to it, what is the rough idea? What generally happens with concentrated sulfuric acid? What is the trend? So we said that the better reducing agents are going to be bromide, iodide. What kind of stuff happens? So they all react. Remember, it's not just bromide and iodide reacting. They all react. Yep, really nice. So the bromide and the iodide, as you get further along, how they're able to reduce your H2SO4, your sulfuric acid, gets more and more significant. So the iodide is able to reduce to the greatest extent. The bromide is only able to reduce a little bit, and the chloride is not able to act as a reducing agent at all. So we're going to look at that in a second in the context of our chloride, bromide, and iodide. So if we start off by thinking about our, for example, sodium chloride. So if we're looking at sodium chloride, is it going to act as a reducing agent with sulfuric acid? And it's the same for fluoride, but we don't really do this experiment with fluoride. It's not able to act as a reducing agent at all. So the chloride ion, it's not really very good at giving away its electrons. It doesn't really want to give it away because it's quite electronegative, chlorine usually. And so if we look at how it reacts, from NaCl and H2SO4, it just reacts as an acid. So we end up with a salt and HCl. NaHSO4 and HCl. It's just going to go down kind of the acid-base reaction. It is not going to work as a reducing agent. And so when we're producing HCl gas, what would we see? What is the observation? White fumes, exactly. So white fumes is the main thing you're going to see. NaHSO4 you probably won't see very much of. You might see something being deposited at the bottom. But main thing you're going to observe is your white fumes of HCl. So remember, sodium chloride, the chloride is not a great reducing agent. You're just going to see white fumes of HCl. Now, if we then take a look at bromide, so we'll go on to the question in a second. We'll think about this is the kind of question we're making sure we can answer. We then go on to bromide. So for bromide, it's a better reducing agent. Well, what's the very first reaction that's going to happen? Is it still going to react as an acid base? Even if it's a better reducing agent, is it still going to react as acid base? Yep. So all of them are going to do that. And so what might the equation for that look like? For sodium bromide and sulfuric acid. Yep. So we've got NaHSO4 and HBr. And if I was to ask you, well, what do you think the equation for iodide is going to look like to produce white fumes? What would that look like? Yeah, exactly. So let's share that's right. So remember, we just memorized that equation once. We're not memorizing three different equations. For the producing white fumes, it's exactly the same for all three of them. Now, someone has written this out wrong. Make sure you don't write this. This is not correct. I just saw this in the comments. We are not producing Br2 in this reaction. Just look at what we're starting from, and you can imagine what we want to have in our products. So the products have to contain the same atoms as the reactants. So we're not going to have Br2 from this reaction, but we are going to talk about Br2 in a second. So you are right in thinking that we're going to get Br2, but it's not going to be from the reaction as an acid base. The Br2 is going to come from a reduction reaction. So remember, this is what the acid-base reaction looks like. NaCl, H2SO4, NaHSO4, and it's going to exactly the same for NaBr. Now, the extra thing you find when you have the reaction of sodium bromide with sulfuric acid is it's also going to make SO2 and water. So with SO2 and water, what we are seeing is that there's also reduction taking place. Now, how could you prove that what we're seeing here, we have reduction taking place? How would you prove that? So when we're making sulfur dioxide, SO2, how are we going to prove that there's now reduction taking place? What could we say? Exactly. So we're going to look at the oxidation states. So just like we did in the last one, and we saw there was no change in the oxidation states, we could look at the oxidation states here. And it's really important that we're able to look at this in the context of oxidation states. We don't just memorize the equations because sometimes the questions expect you to figure it out from the oxidation states. So if we start from this question here, and what I've said is that when we have the reaction between sodium bromide, which is a better reducing agent, it's going to reduce the sulfuric acid down to SO2. So it's going to reduce down to sulfur dioxide. And if we look at what the oxidation numbers might be, and if we start from H2SO4, well, we know that O is 2 minus, so we've got minus 8 here. And we know that the H is 1 plus, so we've got plus 2 here. And because this is balanced, kind of it doesn't have an overall charge on it, well, we know that the S here has to be plus 6. So if we look at the element with variable oxidation state, the sulfur here is plus 6. And if we look at the O2, well, the O2 is going to be minus 4, minus 2 from each of the oxygens. And then the sulfur then has to be what? So it's gone from plus 6 to what? Plus 4, okay? Now, we don't actually need to memorize this equation. What I would say is you can use that to figure out what the other numbers have to be. So all you really need to say is if you're going from plus 6 to plus 4, well, what is the electron change going to be? How many electrons do we need to add to get for 1 mole of this equation, for 1 mole of this change? How many electrons do we need to add on? Well, we need to add 2 because we're going from plus 6 here to plus 4 here. And so that's always going to be how many electrons you have in this equation. And it's always also going to be how many H plus you have in this equation because we always have to have a balance of charges. So however many electrons we have, we also have that many H pluses. And how do you know how many electrons? It's just going to be what is the oxidation change for the sulfur. So we've got 2H plus, 2E minus, and H2SO4 becoming SO2, H2O. And to make sure that this is balanced, we just make sure, well, we have the same number of hydrogens here as we have hydrogens there. So how many H2O are we going to end up with? So if we've got 2H plus and we've got H2SO4, how many H2O are we probably going to need? So we've got H2 in this, and we've got 2H here, we've got 2H here. So at the very least, we're going to need 2. And if we think about 2H2O, is that going to cover absolutely everything? So can we check, is everything balanced here? So we've got SO2, SO4, 1 sulfur. We've got 4 oxygen on the left-hand side. And how many oxygen do we have on the right-hand side? Yes, that seems balanced, okay? Now, this is what's happening to the sulfuric acid. That's the half equation for the sulfuric acid. And this is happening what? Oxidation or reduction? What step are we looking at here? Where we are gaining electrons. Reduction, okay? So if there's a reduction happening in this half equation, well, we have to have an oxidation of the bromine. And the oxidation of the bromine has to represent the same number of electrons. And well, in this case, that makes sense because we've already got 2 Br minus making Br2 and 2 electrons. Well, that's the same number of electrons. These two can balance. And so to work out the final equation, I would then add those together. 2H plus 2Br minus plus 2E minus plus H2SO4. And we can cancel out the 2E minus because it's going to be on both sides of the equation. Plus H2SO4 is going to become Br2 plus SO2 plus H2O and 2H2O. Are we happy with where that's come from? So everyone make sure you are because the next one is a little bit more confusing. did we see where these have come from? So the one thing that you just have to know is the fact that we make SO2. Okay? So we're going to reduce the SO2. That's something that you have to remember. And so I set out an equation that showed how we went from H2SO4 to SO2 and water. That is something that we know. That is something that we found out experimentally. Now, when we know that H2SO4 is reduced to SO2 and water, we are then going to figure out how many electrons are involved in that change, and we know that the number of protons is the same. We also know that if there's reduction happening to H2SO4, well, something has to be oxidized, and it's going to be the bromine. And we've then added the two together to balance the number of electrons changing. So that's where this equation has come from. And so you can see that has been written out like this. And if I cover up where that comes, so what that looks like, what are the changes that you can observe here? So what kind of changes would you observe when this is going on? Yeah, you're going to see red-brown liquid, or occasionally we might see some vapor as well, if any of it vaporizes, but mainly, yeah, red-brown, orange-brown liquid. Either would be fine. The mark scheme usually has all three words, red, orange, and brown. Orange-brown probably better. And we're going to see white fumes from the reaction we mentioned previously. And what about the gas? What are the features of SO2? Does it have a color? No. What are the characteristics of SO2? Yes, it's sometimes described as having a choking smell. So we're going to see a colorless gas with a choking smell. We're going to see steamy fumes. And remember, that was from when we talked about HBr. And we're also going to see this brown liquid, red-brown liquid, bromine. So what we're seeing is that sodium bromide can act as a reducing agent, and it can cause the sulfuric acid to go from +6 to +4. So it is going to cause reduction here. Now, if we think about this exam question, what is the equation? Well, it's just the equation we figured out. What is the observation? Red-brown color. So that's what we just worked out. 2H plus, 2Br minus, H2SO4. And what is the observation? Orange-brown fumes solution. And you can mention fumes if you want to, but mainly solution is the most important bit. So happy with how we get this question right. Yep, we get all the marks on everything so far. Yes? Okay. And why do we add H plus? Well, that is kind of how it reacts. This is in solution, and we've got a solution with sulfuric acid in. So if we've got sulfuric acid, remember it's a strong acid. And so even though it's concentrated and maybe some of it hasn't dissociated, we've just got H plus ions lying around there in the solution because it's concentrated sulfuric acid. It's a strong acid. So there has to be H plus. That's where it's come from. And the number of H plus that react is going to be the same as the number of electrons to balance the equation. Okay, so next, now when we think about sodium iodide, like we said, there's still going to be the acid-base reaction that we talked about before. That's not changing. There's also going to be these reduction reactions. Now, we have the same reduction reaction as before. So what is going to be the oxidation number change for the first one? We've already talked about this one. What's it going to be? Yeah, it's going to be a 2 electron change. So we're going to go from +6 here to +4 here. This is a 2 electron change. So 2 electrons, 2 protons. What about for the next one? So when we have sulfur on its own, what is the oxidation number of just the atomic or the molecular form of anything? So if it's just an atom, just an element, just a molecule, yeah, it's going to be zero. So sulfur on its own is going to be zero here. And the sulfur in H2SO4 is still plus six. So how many electrons change? Six. So we've got 6H plus, 6E minus. Now we look at the last one. We've got H2SO4 plus 6 and H2S. What is going to be the charge on our oxidation number of sulfur in H2S? Minus 2. Okay? So in H2S, in the sulfide, it's going to be minus 2. And that's because the H is going to be plus 2. Like each one is plus 1. And if we're going from plus 6 to minus 2, how many electron change? 8 electron change. So we've got 8H plus, 8E minus. Now, if we were to try and kind of work out the final equations that also included iodine, well, for each of these equations, what we figured out is that here we're seeing reduction of sulfur and it requires these electrons. Now, where are these electrons going to come from? What is the reducing agent that we said was a really good reducing agent? What is it here? The iodine, but not the iodine, the iodide ions, okay? And if one of these, so if one of these equations corresponds to two iodide ions, how many lots of this equation are we going to need to use for the first one? So for this one here, and let me color this one in green, if we were trying to work out the equation for this one here, how many of this equation would we need to balance it for the first one? One of them, because two electrons balance with two electrons. What if we were trying to do it for the next one that I color in orange? How many of this equation would we need? We need three lots of it. So we need to scale it up to 6I minus becomes 3I2 plus 3E minus. Sorry, 6E minus. And we then add that on to this equation here to get the overall. And what about for the third one? If I color that one in blue, how many lots of the equation would we need? Four, okay? Brilliant. So if we try an exam question with that in mind, and these are the equations like we just talked about. So we've got two of them we need, and we've got six of them we need for this one. And you can see that we've tried to balance the H2Os. And the way that we balanced the H2Os was just counting the number of hydrogens like we did before. This is how you get these equations. So if we try an example of a question, and just before we do, observations. No, don't forget the observations. What are you going to see? So, SO2, S, H2S, HI. What are we going to see for each of these? Okay, so one at a time. What is HI going to look like? HI is going to be white fumes, okay? What is SO2 going to look like? Does it have a color? No, colorless gas, choking smell. What is the sulfur going to look like? Sulfur is a yellow solid. Good. What is the H2S going to look like? Okay, it's colorless, but what are we going to recognize then? Yep, rotten egg smell. And finally, what is new? Well, we've got the I2. And well, what is I2 going to look like? And we've talked about this already. So yes, it's purple if it's a gas, but is it a gas at room temperature? Usually. No. So eventually, when it cools down to room temperature, what are we going to see? What does iodine look like? Black solid, okay? So that's a good thing to remember. As we go down the halogens, remember melting point, boiling point, they go up. So the iodine is a solid. It's not liquid. Bromine is a liquid. Iodine is a solid. It becomes darker, it becomes denser, and it has a higher melting and boiling point as you go down the graph. So we've got steamy fumes from HI. We've got black solid iodine, yellow solid sulfur, H2S, which has bad egg smell, colorless, SO2, which has choking smell, colorless. These are the ones that we need to remember. So for AQA, why do I say we should do it the half equation way and not just memorize them? Well, because they could ask you a question like this. So let's give this one a go. The sort of question that might come up that would actually require you to understand where it's coming from. So the first bit should be pretty easy. What is the half equation to go from iodide to iodine? What do you think? Yeah, so iodide is going to be I minus, and we are going to go to I2, and well, we've just lost these two electrons now, so 2E minus. And this is what, oxidation or reduction? So remember oil rig, oxidation is loss. What is happening here? We're losing electrons. So this is oxidation. Now, please, if you're not sure, do not write this on your exam paper, because if you don't know, there's no benefit from getting it right, but there's a harm from getting it wrong. So obviously, if you don't know, don't write anything. So this is the half equation, but yes, this is oxidation. Now we're going to write the half equation for the conversion of sulfuric acid to sulfur. So remember, even if we couldn't remember the numbers, what do we know? Well, we know that we have H2SO4, and we know that we're making sulfur, and we know that we're making H2O. Now, the first thing we're going to check is what is the electron change? So going from +6 to 0, what is the electron change? 6. So then we're going to add 6E minus and 6H plus. Okay? Now, how many H2O do we need? So how many H2O? How are you going to figure it out if you're not sure? Some people are saying 3. What have you done to figure it out? Not just remembering, trying to be logical with this. So how are you figuring out how many H2O? So the easiest thing to do is just count the hydrogens, because the hydrogens are only present in H2O on this side. Well, we've said 6H plus, and we've got an H2 here. So 1, 2, and 6. That makes 8. If you've got 8 hydrogens on the left-hand side, how many hydrogens on the right-hand side? Yeah, got to be 8. So we've got 4 H2O. Okay? So the half equation for sulfuric acid to sulfur, 6H plus, 6E minus, H2SO4 becomes S plus 4H2O. Now, if this is the half equation for iodide to iodine, well, how much do we have to scale it up by to balance the 6? Yeah, we need to scale it up by 3. So that's now going to become 6I minus, and it's going to become 3I2 and 6E minus. Now, if we add those two together, we're going to end up with just the same things as in these two equations, but with the electrons cancelled out. And that will give you what I'm just about to show. So this here, 6H plus, 6I minus, H2SO4, 3I2, S4H2O. Now, what is the other sulfur-containing reaction product? What is the other sulfur-containing? Yeah, SO2, or what's another right answer? H2S. Okay, so either of those two would be fine. SO2 or H2S. Now, the people who are just joining for GLP-1 agonists, what we're going to do is we're going to start, I think, at 10 past or quarter past, because we were a little bit late for beginning with our chemistry. So I think we're going to start at quarter past for GLP-1 agonists, and I'm going to finish chemistry at 10 past. So that gives you a little break in the middle as well. Does that sound fair? Yeah, okay, so if you don't want to do chemistry, come back a quarter past. But you guys all have chemistry exams if you're applying for medicine or dentistry, or vast majority of you. So I would recommend sticking around. Everyone happy with this question and all of the ones so far? What do we think? Yep. So SO2 or H2S, this is the equation, right? Make sure you understand where they come from. Common error that you see on the mark scheme, people write HI. Don't write HI, leave it as H plus I minus. You can't write HI because we do produce HI actually, but it comes from somewhere else. In this scenario, they're both staying as ions. So don't talk about HI for this. We do have HI in a different equation though. And remember, that's going to be this equation here. So this is where the HI comes in, but don't write HI in the equation with the H2SO4 and the H2S. Okay, now, last question about halogens. We've got identifying halide ions. What do we know? What do we do to identify halide ions? Silver nitrate? Yes. What else can we do? Acidified silver nitrate? Very nice. That's an improved answer. And what else can we do? Dilute and concentrated ammonia. Okay. So, well, silver nitrate tells us anyway, no? So, silver nitrate gives us the three colors. Why do we need the ammonia for? That seems like a waste of time. Yeah, because the colors are hard to differentiate. So the colors are pretty similar. If we look at them just now, let me show you what the colors look like. These look pretty much identical to me. And let's not look at the answers. But these three colors, they look pretty much the same. That's why you use ammonia. Because how are you going to tell the difference between bromide and iodide? They all look a slight shade of white. That's why we're going to use the ammonia. So we've got a question here. A solution that is thought to contain chloride and iodide are tested. Immediately, as you read the first part, what are you thinking? What are the two colors? Chloride and iodide. Yes, white and yellow. So the two extremes, okay? We've not got bromide, no cream. White and yellow. So even before you've read the information.
Sir.
Make sure you mute yourself, Yuvraj.
Sir.
So we're now going to think about a reason for the use of each reagent and why we're seeing what we're seeing. Okay, so let's start with the first one. Dilute nitric acid. What is the dilute nitric acid for? So think about it. We're making precipitates. Why might we want to be adding acid? Removing any impurities? Yes. What kind of impurities? Carbonate ions? Maybe what other kind of ion? So carbonate or maybe hydroxide. So we're thinking about, can we get rid of any carbonate ions? Can we get rid of any hydroxide ions? Next, we're adding aqueous silver nitrate. Why are we adding aqueous silver nitrate? Yes, because it's going to make the precipitates that are different colors, okay? Then we're seeing a pale yellow precipitate forms. Where does the pale yellow precipitate come from? Yep, that's going to be the iodide. Now, we're going to add excess dilute aqueous ammonia. Now, which one of these dilutes in excess dilute aqueous ammonia? Yeah, chloride. And some of the precipitate dissolves. So that's going to be your chloride that's dissolving. And a darker yellow precipitate remains. Let's explain that observation. Why is the precipitate that remains darker yellow? What's making it darker? Well, because it's just the iodide. Before it was the chloride as well. So you had a mixture of white and yellow. Now we have just yellow. So because it's pure yellow, that's going to look darker than a mix of white and yellow. So let's think about those colors again. We've got silver chloride is white and it dissolves in dilute ammonia. Silver bromide is cream, but it needs concentrated ammonia. And silver iodide, it just doesn't dissolve and it's pale yellow. Now we use the ammonia because we want to make sure these subjective colors, we don't get them wrong because bromide and iodide are pretty similar. What are the equations? Pretty self-explanatory. So we've got Ag plus Cl minus AgCl, Ag plus I minus AgI. Notice you only actually needed one of them on the mark scheme to get the mark for the equation. And the second equation, you have to show that it's dissolving. So you're going to show AgCl and it becomes AgNH32 plus Aq. You can show that. Or if you've not done transition metals yet, and this would be confusing, if you are just shown AgAQ, this would also get you the marks. So either way would be fine. But key thing is you have to show that AgCl in solid is becoming aqueous Ag and aqueous Cl. And what you're seeing here is a transition metal complex. Now, you only do this in year 13, and that's why on the mark scheme, if you had just put AgAQ, that also got marks. Is everything else on this screen you're quite happy with? Does everything else make sense? Yep, brilliant. So that is pretty much it for your halogens. You do have a little bit on uses of chlorine. Most of them are very much common sense. So why do we add chlorine to water? Well, to kill the bacteria. Chlorine is toxic. Why do we still add it to water? Well, because a tiny bit of chlorine is going to do a lot less harm than lots and lots of bacteria. So that's pretty self-explanatory. You do need to know these reactions, and there are a lot of kind of short mark questions that just ask you about the reactions of chlorine with water and chlorine with alkali. So chlorine with water, gonna make HClO and HCl. Chlorine with alkali is going to make NaClO plus NaCl plus H2O. So very similar pattern, HClO, HCl, NaClO, NaCl. Now, what is slightly unusual about this reaction? Why might it be different in certain circumstances? So this is something that is on the AQA specification. In sunlight, what changes? So chlorine plus water, what happens differently in the sunlight? Anything we can think of? So the reaction is actually different. In sunlight, we don't make HClO plus HCl. We actually make HCl plus O2. Okay? So that's the only thing that sometimes people trip up on. Chlorine plus water usually is going to make HClO plus HCl. It's the same for bromine, same for iodine. But in sunlight, it makes HCl plus O2. So that's something you'd like to write down. In sunlight, we've got HCl plus O2. But normally, we have HClO plus HCl for water, or NaClO plus NaCl plus H2O for alkali. And in particular, what we're talking about is cold dilute aqueous alkali. So with cold dilute aqueous alkali, NaClO, NaCl, H2O. Otherwise, HClO, HCl, that's going to be with water. But in sunlight, it actually makes HCl and oxygen. Happy with the difference? And that's just for chlorine. Yep. Okay. So I think that is a pretty good run through for your halogens. We have missed out a little bit for group two, but group two, I would say, is mostly self-explanatory. I would take a little look through the slides. And if anyone sticks around after we do GLP-1 agonists, then at that point, I'm happy to go over any questions about that too. So we'll start GLP agonists in 2 minutes, or maybe a couple more if you guys want a break. I hope that you now know a little bit more about your group 7